Maciej Szymanski is a physicist and author known for his groundbreaking book Can't Physics Be Simple, in which he challenges established paradigms in fundamental physics, offering innovative hypotheses that address enduring paradoxes and mysteries in the field. And we've got Maciej on the line with us here. How are you today?
Yes, pretty good.
Excellent. So, can you tell us about the three basic hypotheses that form the foundation of your book's EE theory?
There are four hypotheses, which the first one I call the fundamental law hypothesis. It states that laws of nature do exist independent from the human mind. Fundamental means that the laws of nature have no underlying principles. This hypothesis leads to the separation of physicist's mind from nature, which means separation from fundamental physics. It is a purely philosophical hypothesis. It cannot be proven or disproven by any experiment. The second hypothesis states that an object comprising a finite amount of matter cannot interact with another object over an infinite distance. This hypothesis resolves the paradox, which implies that a finite amount of matter can have an infinite range of interaction. That paradox is included in the current paradigm of physics. In theory, it can be experimentally proven. In practice, however, it would be very difficult to prove it given the currently available experimental techniques. The third hypothesis just augments the second. It states that the total range of interaction of an object is proportional to the amount of matter that the object comprises. The base for the fourth hypothesis is the result of the famous LIGO experiment. This hypothesis states that an abstract entity that exists in physicists' mind only, space-time for instance, cannot affect matter. For instance, LIGO arms in the LIGO experiment. The book is primarily about the consequences of those four hypotheses.
So how does the fundamental law hypothesis impact the execution of fundamental laws of physics? And what are the constraints it places on these laws?
First, let me talk about the constraints on the execution of the laws of nature. I consider the laws of nature and the fundamental laws of physics to be the same thing. According to the fundamental law hypothesis, the laws of nature cannot have underlying principles, as I just said. Consequently, nature, who executes those laws, cannot own and operate any devices, such as clocks, rulers, weight scales, electrometers, etc., because any of such devices operates according to some principles. As a result, nature cannot make any measurements. Therefore, she is unable to know the values of physical constants and other quantities. Moreover, nature cannot have a memory. She cannot have the concepts of space and time. She is unable to make decisions. Furthermore, she cannot know mathematics, which means that the fundamental laws of physics must be non-mathematical. Now, looking at those constraints from another perspective, they clearly represent attributes of the human mind, since the physicist can remember, makes decisions, measures things, do mathematics, and so on. Now, you asked about the execution. Now, concerning the execution of nature laws, the fundamental law hypothesis implies that we will never know how nature executes her laws. That is, for the laws of nature have no underlying principles. One cannot possibly know how a law that has no underlying principles is executed. It is impossible to know.
Now, your book discusses the need for a successful physical law to be consistent with the laws of nature and exclude the possibility that nature possesses any attributes of the human mind. So, can you elaborate on this idea and why it's crucial for physics research?
First, the need for the consistency of a physical law formulated by a physicist with the physically existing or physically real laws of nature appears to be intuitively obvious. As I already mentioned, nature cannot possess any attributes of human mind. Explicit exclusion of that possibility isn't absolutely necessary or crucial to formulating a physical law. I think of that exclusion. Remember, the exclusion is nature doesn't have an attribute, cannot have an attribute of human mind. So I think of that exclusion as a guide to formulating a successful physical law. For instance, as far as I can tell, the quantum theory was developed in agreement with the exclusion rule. I believe that a physical law has a better chance to be successful if it explicitly forbids nature to do something she cannot possibly do, which means forbids nature to have an attribute of the human mind.
And how does fundamental law hypothesis's implication that the laws of nature cannot incorporate space and time affect our understanding of the universe?
Yeah, here the answer is quite simple. It is important to realize that understanding of the universe belongs strictly to the human mind. As far as we can tell, nature has neither a need nor a desire to understand the universe. Nature not realizing space and time doesn't affect in any way our ability to understand the universe. However, to understand the universe, we must account for nature's inability to realize space and time. In other words, in trying to understand the universe, it is absolutely crucial to account for the fact that nature doesn't know space and time. So that's my answer, and I think that the affair is quite simple here.
Now, your book controversially states that nature is as simple as binary, 0 or 1, and that the laws of nature include the second law of thermodynamics, the action-reaction law, and the material-energy conservation law. So, can you discuss why these laws are fundamental and their implications for physics research?
Now, you mentioned controversy, and that's very important here. So let me talk about the controversy. The suggestion that nature being as simple as binary 0 or 1 appears to be controversial indeed, but only from the perspective of the current paradigm of physics. That paradigm implies that nature is at least as complex as human brain, as human mind. This is a strongly biased viewpoint with no evidence of any kind that could support it. I think it goes back to the authors of the Bible who claimed that God, which to me means nature, created man in his own image. Therefore, according to those authors, the mind of God, that is nature, is as complex as that of the physicist. Remember, God created man or physicist in his own mind. That prejudice concerning the mind of God is discarded. The controversy about nature being simple in extreme disappears. Regarding now the laws of nature, those laws are fundamental because they have no underlying principles. The implicit implication of that statement of the laws of nature is that any other law in physics exists in physicists' mind only. It is not a part of nature. It is an abstract law. The execution of it cannot cause any physical effect. To put it another way, nature cannot realize and act upon the physical laws that were invented by physicists, even if those laws are highly suitable. Nature is way too simple to realize, to understand, and to act upon laws formulated by physicists. That, I think, summarize the thing.
How does your book approach the issue of mathematics in physics, and why do you believe that language is the ultimate governing language of science?
Okay, let's start with the fundamental law hypothesis, which implies that the laws of nature must be non-mathematical. On the other hand, the experience clearly shows that mathematics is a necessary tool to do descriptive physics. I call it applied physics or mathematical physics. It is the applied physics that made the technological advances possible, the incredible advances, technological advances. One might might say that it is the use of mathematics that allowed for the incredible advancement in technology. Saying that mathematics is or isn't the ultimate governor of physics is perhaps not the best impression. It was originally used by somebody else. The observation, rational reasoning, and mathematics are needed to advance the applied physics. The observation, rational reasoning, and language, rather than mathematics, are necessary to advance the fundamental physics. The fundamental physics seeks to explain rather than describe physical effects. In advancing fundamental physics, we must not use mathematics simply because nature doesn't know it.
Now, can you discuss some of the well-known mysteries in physics that you suggest can be explained from the consideration of fundamental law hypothesis? And how does this philosophical notion yield pragmatic results?
The explanations of most physics mysteries that I discuss in the book require the consideration of both the fundamental law hypothesis and one or more laws of nature. Some examples. The mystery of the force of gravity, that's my favorite mystery, which is proportional to the product of masses of two interacting objects. It fascinated me first. That product was introduced in Newton's law of gravity that proved to be highly successful. It didn't make any sense to me until I realized that one cannot tell that one of the masses contributes to the force of gravity more than the other mass. And that is exactly what the fundamental law hypothesis requires from nature, as nature cannot possibly know an amount of mass. She doesn't own a weight scale. She cannot measure things. Another example is the mystery of quantum entanglement. The fundamental law hypothesis implies that nature doesn't realize space and time, as I already mentioned a few times. Therefore, a quantum entanglement effect has to be generated regardless of space and time. Einstein didn't like it. He famously called it a spooky action at the distance. However, as I just said, nature doesn't realize space and time in the first place. As a result, the mystery of quantum entanglement can be very simply explained. I cannot go into details, it would take a while, but it's explained in the book, I think at the senior high school level. Another mystery is the speed of gravity, which according to the current physics equals the speed of light. However, that is not possible according to the fundamental law hypothesis, because the laws of nature cannot incorporate speed, the concept of speed. Speed is defined in terms of space and time. The logical conclusion, therefore, is that the speed of gravity is infinite. From that consideration, another mystery, the mystery of an imaginary force of inertia, can also be explained. Say a driver in an accelerating car does feel the force of inertia, which, according to Ernst Mach, is the strength of driver's interaction with distant stars, with distant masses. The driver feels it immediately after stepping on the gas pedal. Therefore, the mystery of the inertial force, which is imaginary in current physics, that means exists in physicist's mind only, can be easily explained by driver's interaction with distant masses. That is consistent with the infinite speed of gravity. Now, note this, the effect that is the pressure on the back of the driver is as real and not imaginary as the force of inertia. In today's physics, the force of inertia is imaginary, and yet the driver feels the pressure on his back. Something is not right.
How can your book's ideas and hypotheses impact current physics research and potentially contribute to breakthroughs in the field?
I think it is reasonable to suggest that physicists' senses have developed in response to the instinct of survival. That's not only my idea. somebody else was saying the same thing. A physicist in researching physics can be subconsciously guided by his senses. For instance, he or she may sense three-directional space and consider it to be the stage on which physics is playing. However, since nature is unable to realize space that the physicist senses, because she has no instinct of survival, nature is expected to execute her laws in instance of space. Instance of space, by instance of space, I mean directions in space. As nature executes the second law of thermodynamics in interaction between material objects, she executes the law along each of the trillions of directions, connecting the trillions of components of the interacting objects. And she executes that in each instant of time that show the enormous power of nature, controlling with a perfect accuracy trillions of interactions along trillions of directions. Now, using human's perception of three-directional space, the clever physicist invents Fourier's law for heat conduction to describe the execution of the second law of thermodynamics in three directions only, in three directions of space. The physicist can do it because of his sense of three-directional space. Of course, working in three directions rather than trillions of directions is much simpler. That's why I call the physicist the clever one. Another example of the importance of human senses in doing physics is so-called cosmic microwave background radiation. Physicists have no sense of this radiation, and humans have no sense of this radiation, for it doesn't present a noticeable threat to survival. Yet, once discovered in 1965 by a chance, it quickly became apparent that the cosmic microwave radiation has to form a base of our understanding of the universe on the largest scale. In that case, it was the lack of human sense concerning cosmic microwave radiation that prevented our appreciation of a critically important feature of the universe. There are more examples of the connection between physics and physicist senses, but it would be too much to talk about everything here.
And what are your plans for further research and exploration in physics? And how do you plan to build upon the concepts and hypotheses that you've presented in the book?
I expect no significant breakthroughs in the field of applied physics. I am quite certain about it. However, it seems to me quite possible that a rational appreciation of fundamental physics could lead to a simplification of the physical laws, the laws that have been derived by physicists. Just simplification of the laws, nothing new. Concerning the simplification, I think of abandoning the search for the theory of gravity could lead to a further and significant advancement in physics. That idea, the theory of everything, which is to find a set of equations that describe everything, presents a purely mathematical exercise according to the characteristics of from the fundamental physics that I propose. It's just mathematics and connecting general relativity with the quantum theory will not advance our understanding of nature, our understanding of physics.
Well, where are we able to find this book, Can't Physics Be Simple?
The book is all over the place, published on many platforms, Amazon as a first example.
Excellent. Well, many thanks for joining us today. It's been great having you here.
Oh, thank you very much.